is Thermocalc and AvPT. So this talk is going to be presented by Professor Dave Waters. So a little bit of a background about Dave. Dave is a recently retired professor in the Department of Earth Sciences at the University of Oxford. He obtained his bachelor's and master's degree at Cambridge, and then went on to do his doctorate at Oxford. His research interests are broad, as you can anticipate. They include geothermal barometry and phase equilibrium modeling, fundamental processes of metamorphic recrystallization, and the record they leave in the microstructures of metamorphic rocks, and then applications of metamorphic petrology from thermal aureoles to young mountain belts to subduction zones to ancient granulates. So basically, Dave's done it all. And I think perhaps as important as all these contributions has been his role as an educator of a generation of some of the leading metamorphic petrologists in our community. So I'd like to turn things over to Dave Waters.
Right, hello. I hope you can see a screen there. And it should be my title screen. And so yes, it's Dave Waters here in Oxford. And I'm going to talk about Thermocalc and its facilities. I hope you can see there's a little kind of outline at the bottom of the screen. I hope it's not covered up by whatever Zoom does. There's quite a bit to talk about, and I'm afraid I most likely will run over the 45-minute slot that's on the timetable, but I hope we can cover things that I skip in the Q&A session. First, a bit of a disclaimer. I'm a user. I'm a sort of practical practitioner of a petrologist. I've not been involved in the development of the program or the data sets or the solution models. I hope that puts me in a position where I can help a little give you an impression of how the software gets used. Now, Thermocalc goes back a really long way. It started really in the PhD project of Roger Powell in the early 70s in Oxford. And it began with a suite of Fortran programs that sat on the university mainframe. And actually, that's where I came in too, because encouraged by Roger's thesis supervisor, I started using these programs and calculating activity-adjusted curves via, thankfully, a remote terminal, such as put some hardware on the right, so you can see the kind of evolution of hardware that we've used for calculating thermobarometric data over the years. So we had one of these teletypewriters in the corner of a lab, and that's what I used in the early middle 70s to calculate my first data. What happened later was that Tim Holland got involved with developing the internally consistent data sets in the 80s. But the Thermocalc program itself wasn't released publicly until 1988. And its focus at that time was mainly on thermobarometry. And this was the beginning of the average PT method, which got a lot of use in the 1990s. As I say, it was the main focus for a good while. What's happened since then are things like the enlargement of the data set. So the milestones for that, Pierre's already mentioned them in 1990, 1998 and 2011. Papers published by Holland and Powell. Solution models are developed. They've gradually become more complex and we hope more realistic in terms of their application. Recently, there have been quite significant changes with the introduction of Thermocalc version 3.5, current version, various enhancements, various changes to file formats and scripting, and I'll hope to say a little bit about that. So if you're looking for information, then there is a current site that's at the top of the slide here, which is now called the HPX EOS and Thermocalc. And the header for the website is over on the right there. This is fairly new, so it's growing. And it discusses and describes the current versions and best practice as they stand now. And so if you want information on the older versions, the older data sets, and some of the tutorial materials and other materials, then you may still have to go back to the older versions, some of which were on the website at Mainz and in stuff that was distributed from workshops. But you will find, thankfully, an awful lot of them are available through the Science Education Resource Center at Carleton College, and various links to that there, and I hope you find them useful. You may well still have reason to use older versions of the program, and it's already come up that people are still using dataset 5, for example. How does it work and how is it different from other packages? Yes, there's some important differences. First of all, Thermocalc is not a free energy minimizer. It's an algebraic system. It solves sets of nonlinear equations. And to do that, because these equations are pretty complex, you need to provide starting guesses. Default starting guesses are supplied, but you may find as you go along in calculation the need to change them from time to time. It's another important difference in principle. From the point of view of phase diagram construction, if you're using a free energy minimizer, then boundaries of the assemblage fields are going to be interpolated from essentially gridding or otherwise pinning down the boundaries themselves. With Thermocalc, however, the idea is that you calculate these boundaries directly. You know, the equations that are solved for the boundaries. And in terms of the method, therefore, it's calculating individual equilibria of specified variance. These may be lines, univariant lines on having supplied a bulk composition to the method. They may be points, which are the corners of assemblage fields, or you can actually grid an individual field with an array of PT points and pull the information out for those within a field. So the focus is on lines and points. The other important feature is that you build up a diagram incrementally. You can't, there's no way of building the entire diagram in one go. So on the right, there's a picture of a partly finished diagram, and you can see that I actually started here in a convenient low variance field. I'll say a little bit more about that in the next slide. And then the idea is that you build up incrementally from that point. Thermocalc actually has 3 PTX calculation modes. Phase diagram calculations are what most people are likely to focus on, but there are rock-oriented calculations which will take data from real rock, and that's where average PT comes in. And there's a mode 3, which I will mention as well, where you calculate all the reactions in a system, and I'll show you just towards the end that actually can be quite a useful and almost inspiring way of looking at some of the equilibria you might want to use. So, okay, let's start with mode 1, which is the phase diagram mode. And again, at the top, just a reminder that we have the 3 modes. So Thermocalc in mode 1 is designed for calculating phase diagrams. It has 3 crucial input files. There'll be a preferences file, which sets the project name, tells it what database to use. There's a file which contains the solution models called the AX file. A is for activity, X for composition. So that's the solution models that it's going to use. And there's a script file, which is the one that's most under your control as a user, because you're going to use it to put in various parts of data and instructions, operating commands, and so on. I'll show you bits of examples of those as we go along. The interface is the console or terminal window, and and on the right there, I've got a screenshot from a run that I started about a month ago, and you can see a little bit of what it consists of. The style is rather question and answer, so there's some output information at the top there, just what the program is going to do. It starts asking you questions. You can select the phases you're going to use in a particular run, and so on. Increasingly, what you do interactively like this can be substituted via scripts, or can be built in your script file to start with. And the ultimate aim is essentially to be able to run Thermocalc without having to use the interactive mode. You should be able to essentially run it entirely via scripts. And that's part of the development that's been ongoing at the moment. There are output files that I'll go on to in the next slide. I think we're ready for that now. We have then some output files that give us basic output text files, give us a log of essentially everything we can see on screen. There's an output file with a suffix O. I should say all these files begin with the prefix TC. Suffix O is the output file you may look at most of. It's a result of the calculations that you've asked it to do, minus the interaction. There's a DR file, which is meant for use with the DrawPD, the accessory program that will produce graphics output for you. The latest versions introduce further output, some of which is interesting and important. The IT file is one that actually lists the solution model codings for the phases that you use in the calculation. And that's potentially pretty important, either for you or for anyone else who wants to reproduce your diagram, because it will give exactly the solution model codings that have been used and should reproduce the diagram for you. The IC file is a full listing for each individual calculation, phase compositions, proportions, site fractions, thermodynamic properties of phases and end members, and that's then it will. I'll show that again, and that makes it gives you the full list of output that you might require. On the right, then we've got a sort of truncated form of what the output looks like in the O file and what you'll see on the screen. This one was for locating the corner of an assemblage field where staurolite and chlorite modes go to 0. So in terms of databases and solution models, we have really two options at the moment for databases. The one which is normally called dataset 5, dataset 5.5, latest main revision 2004. Dataset 6 is the released in 2011, currently on dataset 6.2 or 6.3 for some applications. And there have been fairly major changes between dataset 6 and data 5. Might probably have more to say about that. Various of us will have more to say about that later. The solution models are now rebranded as the HPX-EOS, that's Holland and Powell composition equations of state. And they exist as packages of internally consistent models. And they've been kind of organized and rationalized to the point where you can't really mix and match anymore without possibly compromising the database. They're designed for particular rock compositions types of problem. Solution phase, again, there's a difference between this and certain other approaches, is described by an independent set of composition parameters, and normally loosely called X, Y, Z parameters. And on the right-hand side, I've given an example of garnet, for an example how that would be coded. And with 5 end members here, you're going to need 4 independent parameters to describe them. And in this particular case, the X for garnet is the mole fraction of iron 2+ in the large cation site over iron plus magnesium in that site. The Z is mole fraction of calcium in that large cation site, and so on for manganese. And F for ferric iron is the mole fraction of ferric iron in the what's otherwise the aluminium site. There's coding in here that will give you the proportion, therefore, of pyrope in the garnet, the sort of cake slice amount of pyrope in the garnet, shown the example here for the mole fraction of magnesium in the site, in that large cation site, and the coding as it would be used for the thermodynamic mole fraction, ideal mole fraction, if you like, ideal activity for pyrope in the garnet. And you can see they look quite complicated, but they're going to be turned into algebraic expressions inside the program and used in the calculation. Propagation of uncertainties is interesting because it's something that was built in to the data set from the outset. Those uncertainties are based on the least squares regression of those fundamental data set enthalpies together with their covariances, and so that's where that comes from. But remember, it's just the enthalpies that have those covariances associated with them. And Pierre has already mentioned what happens if we are not taking into account uncertainties or potential errors in quantities like the entropies. There's capacity for uncertainty, estimating the uncertainty on activities from the solution model parameters as well. It would be pretty complicated to do that for a given the complexity of the sum of the models. So there's a somewhat generalized procedure that's based on multiplicity of the most significant site in any given model for estimating those kind of uncertainties. And both the data set and the activity uncertainties are also applied in the average PT thermobarometry, which we'll see later. Fundamentally, at the bottom line is that the authors are concerned, so Powell and Holland are concerned that we don't underestimate the uncertainties involved in the thermodynamic calculations. So they're, in a sense, erring on the side of caution. I'll be saying a bit more about this when we come to the uncertainties session on Wednesday. So a variety of calculation types that can be used. PT projections or petrogenetic grids is one of them. Phase diagram calculations, that will be most of what I talk about. It's probably the one utilized by most people. Mode boxes, ways of assessing modal proportions as they change with pressure or temperature. That's again built into mode 1. Compatibility diagrams can be calculated with mode 1. It's described in all the documentation, and there's an updated tutorial produced by Simon Sean that can be seen on the current website. And there is also some provision for free energy minimization. Having said that, that's not a feature. We'll see in a moment how it can be achieved and how you might well need it to start a program going. The diagrams on the right are there because the mode boxes and the compatibility diagrams are not something that I have time to talk about further. So just starting with PT projections or petrogenetic grids, the kind of things that we used to draw some time ago quite frequently. So these are diagrams that show all the stable reaction curves and invariant points regardless of bulk composition. And and these were helpful for simple systems. They used to be really quite important for exploring new systems we didn't know very much about, but they do get very complex. These days, I find that I really only use them for simple teaching examples. There's an example on the right, which is for the classic KF-MASH grid for metapelites that's been around in the materials, Thermocalc materials for quite a long time now. It makes a nice example. It shows and it underlines the fact that these are linked bundles of stable reaction curves arranged according to Schreinermacher's rules. And as for all applications of Thermocalc, really, as a user, you need to be familiar with the geometrical principles of phase diagrams like Schreinermacher's rules. So we have a bundle that obeys the rules around this invariant point up here. On this diagram, you'll also notice that some of the reactions terminate, and they terminate because they've hit an end-member system. Most of these ones down at low pressure are because they've they've hit the iron end members of iron magnesium reactions on this diagram. When you come to producing or examining a isochemical phase diagram, this again is a nice simple one for metapelites and KF-MASH. Again, it's from the old materials. This is what you get if you now insert a bulk composition of a rock that you want to investigate. The script instruction in their pseudo section will calculate the relevant information for you to calculate a diagram like this. Again, there's bits of geometry you need to understand, because what this calculation does is find sections of curves that your rock composition will see, that will be experienced by the rock you're interested in. And that means that under those circumstances, all the calculated phase modes are positive or zero, and they're zero when certain when particular mode reaches a certain boundary. So I've highlighted an intersection on the right on that boundary just to show, make the point of the geometry here. This is a system with muscovite quartz and water involved, and we have a divariant assemblage here with chlorite, garnet, and biotite in addition. And that boundary then is that corner of that field involves a point that's now sort of constitutionally invariant, and that divariant field makes contact with two trivariant fields, and opposite it there is a field here with just chlorite, muscovite, quartz, and water, which is a quadrivariant field. And you'll notice that there are metastable extensions for two of those boundaries, which penetrate into the low variance field. But the two boundaries that are relevant to that low variance field actually terminate at that point there. That's something you need to be aware of, because it means that if you're following a boundary like this, you can enter a field here without knowing it. If you're following that boundary, it becomes metastable. And so this is one of the things you need to be alerted for, particularly in Thermocalc when you're calculating these kind of diagrams. Next question, I guess, is how do you start? To start, you really need to know, ideally, some sort of nice low variance field that will allow you to begin and work outwards. And to begin with, it would be a good idea to actually do some free energy minimization. And there's this command, do-gmin, or dogmin, as some of us call it, which has effectively a brute force method of free energy minimization. It takes the phase list you've provided, and it goes through each possible mineral assemblage to find the lowest, to find the mineral assemblage has the lowest free energy. Unlike other packages, it is actually up to you to include all the phases you think may be relevant for a particular calculation. And there's a trade-off involved here, because the more phases you involve, the more likely you are to cover all the ground, but the longer it will take that brute force method to find the lowest free energy. If you do it for just a single PT point, you'll get quite a lot of detail, and it'll list the whole sequence of equilibria in order of increasing free energy, so you can see what free energy surfaces are lying close to or just underneath the minimum free energy one. However, to get started, you might want to do a traverse across the scope of your diagram. And so on this slide here, I've put an isobaric traverse at 5 kilobars across the diagram I was interested in computing. That has logged the phases present in the different assemblages as you go across there. And you might wonder why I've highlighted some sort of 2/3 of the way down there. That's because it looks like there were some fairly rapid changes there, and that could be the hint of a good place to start. So this might be where we want to focus, and we'll find low variance fields somewhere in that neighborhood. So that's what happened here. Started from a convenient low variance field. It was this one here, this narrow field, and I've worked outwards from that. It's bounded by 3 invariant points here, And from each of these, you can find the other curves that you might want to construct along. So there's a straw light absent curve that you can calculate along here. One that's actually chlorite absent that works along here, and so on. So you have to keep Vandermarker's rules in mind, find the curves to work along, and away you go. And it really does help to sketch your developments with a pencil and paper, or have a spreadsheet package open and paste interim results. Okay, it's laborious work, but it delivers insights that you won't get, I would argue, if you use a free energy minimizer. Note that each line you're calculating here represents the incoming or outgoing of one phase at a time. And for example, you might need in this case to be alert for some other phase to appear, which on this side of the diagram is going to be epidote. And you'll then find that the incoming of epidote makes a whole network of lines that form a continuous path, or perhaps an enclosed area for that phase. And you simply learn as you go along. And similarly, you've got straw light bearing assemblies on this side of the diagram. So away you go. And now I'm going to run through some of the other types of diagram that you can calculate that are essentially these, not exactly isochemical phase diagrams, but phase diagrams that now you can include a composition variable. This one is a set of diagrams that show volatile phase with two M-member compositions, H2O and CO2. So you can use this for carbonate rocks, and here this particular example is for marbles and calc-silicate rocks and some assemblages from the Himalayas, from a paper published a decade or so ago. And so volatile mixtures are one thing you can use as an X coordinate. You can use a composition variable, a single variable like magnesium number, or Mg over Mg plus Fe ratio. So that can be useful for overview of a system with ferromagnesian phases, find out how that varies. Calculations on these diagrams are made at discrete values of the x-axis. When it comes to locating the actual invariant points, the corners of fields here, it's a little bit more complicated because it'll require some interpolation. But when you come to plot these using DrawPD, the plotting program, it has ways of finding those intersections for you. Next thing you might want to do is plot isopleths on your diagram. And you can plot isopleths for composition parameters. You can plot isopleths for modes. Each isopleth is treated as a univariant curve. Again, the catch here is that each assemblage field must be treated in turn, because of course you're asking Thermocalc to make calculations on a specific assemblage with a specific variance, and so within that applicable field it will calculate the isopleths for you. And of course it may stray into the metastable parts of that field as well. Sometimes that can be actually helpful to see what's going on. Having set that with a script that in the latest versions is called isopleth, in earlier versions it was called set iso. You choose a parameter from a list, set a range of values and interval, and then away you go. And it is possible to calculate the intersections between isopleth and field boundary, which can be determined by setting in addition the relevant phase for that boundary to a zero mode, and it will find the point on that boundary that's relevant. Again, calculating isopleths and organizing the data output can be labor intensive, and you won't want to do it for tiny fields, but in practice for narrow fields, an example might be this one on the diagram here on the right. You can get what you want simply by joining up the matching points, the matching intersections on either side, and that will do for you. Another possible catch is that for derived parameters, and my favorite bugbear is not being able to calculate the pyrope isopleth for garnets which are formulated in the current HBX EOS, which doesn't involve pyrope as a separate composition parameter. Mode isopleths, a little bit of an extra quirk with mode isopleths. First of all, they have rather idiosyncratic units. They are in molar units, they've been normalized to a 1 oxide molar basis, which converts them into things that are not far off volume proportions, but of course they're not exact volume proportions because the densities, the phases differ. But you can convert them to volumes using density or molar volume data if you need to. Mode contouring in Thermocalc works like composition contouring, but it does have other issues and slightly counterintuitive scripting if you want to get it to work. And there are normalization effects. The normalization effect I want to highlight here is what I call the H2O effect, where if your system is actually calculating an H2O phase, either with moles H2O specified or in excess, nowadays with the new versions you have to specify the H2O content. It will normalize these for you and exclude the H2O mode. But if you want to set a mode contour, its value relates to that total system, not just the solid phases. In other words, if you put in a mode that you want to contour, you'll find that your normalized result gives a mode value which is different from the one you put in, which is annoying. You can come to terms with that simply by saying, well, okay, all I'm trying to do here is get an impression of the distribution of volumes across the diagram as a whole. But again, you need to remember they're not strictly volume modes, and they do not always correspond to the contour values that you put in if the H2O effect is working. And there's a partial solution for that in this supplementary program TC Investigator that I'll mention later. If you're interested in the compositions of your phases, and I would argue that you should always look to compare the calculated phase compositions with the ones in your real rock, then you can. In principle, the XYZ parameters in the standard output do that for you, but they're not in a convenient form necessarily to do it. A lot of manipulation involved there. But in other forms of output, in particular in the IC file now, you'll find a thing called the RBI matrix. You can ask for it to be outputted in the standard output with a script, and that basically is a matrix of the molar compositions of each phase. And you can see the example there in the lower half of the slide. And for the system as a whole, so it will calculate a molar bulk composition for you. And that's useful if you want to put that back into another calculation, particularly because you can adjust it and do some fractionation calculations in that way. The extended output in that IC file will give the RBI block for you, and it'll also output a lot of other parameters, the XYZ phase compositions, variables, site fractions for elements in each phase, compositions in oxide units for the bulk and each phase, and the molar mode of each phase, and thermodynamic quantities, and in the bottom block, activity details for each member in each phase. The list on the right there just puts in a sort of sample of some of the blocks of information that you can get out there. And that's, I say, that's roughly equivalent to the full output that you can get from Theriac and I gather also from Perplex. I hinted earlier that it's not impossible to do fractionation calculations. It does require manual adjustment stepwise of the bulk composition that you can get from the RBI output. So you've got to do it one step at a time, manually change the bulk composition, run it again. And also because the calculations are phase assemblage specific, if you hit a phase boundary, you've then got to change the mineral assemblage and start again from the boundary. It's not impossible, but it's hard work. There's an example here that I made quite a long time ago now, that's more than a decade old, but it was a way of calculating a fractionated garnet PT path for a Himalayan metapelite. There are hints of forthcoming extensions that will make that easier, so just check the Thermocalc website for information on those, and down the line some information about when they're going to become available. Modebox is something that the output now is I understand at least, is now generated in a form that will make it easier to calculate these. But you can always use your own auxiliary program to plot the mode data. Here's one here that I made earlier manually just by collecting the results and making preliminary plots in a spreadsheet, and then you can tidy them up in a graphics app as you wish. The main graphics output program, though, is DrawPD, stands for Draw Phase Diagram, and that's bundled with the Thermocalc package. So you'll have it if you've done the big downloads, and the executable file is called Draw, or it might have a version number attached to it. DR118 is the latest one. It takes output from that DR file, but it does need some editing to make it into an input file for DrawPD. There's a template file which is pretty helpful, and there are notes and PDF file, DrawPD PDFs, that are also helpful. And you should be able to get up and run and produce a diagram like the one on the right-hand side here. That's raw output from the DrawPD program. The output is as an EPS file, which you can then drop into a graphics editor, vector graphics editor. And actually, because some EPS files are in fact text files, you could go into the EPS file itself and do some modifications. I've not been brave enough to do that, but in principle, it could be customized. A couple of other auxiliary programs. The program AX by Tim Holland. Again, A for activity, X for composition. This was a way of calculating activities for N members from primary analytical data for use in average PT calculations, and it uses or approximates the then current solution models at the time that the AX program was released. And there are releases that go through until the beginning of dataset 6.2. But with the current versions, with dataset 6 and Thermocalc version 3.5, within 3.5 itself, you will need to use the HPX EOS itself rather than AX. It's designed to use the composition parameters that you would use for this diagram calculation. So that's one reason why conceivably you might want to keep two versions of Thermocalc or two versions of the approach if you're going to use the average PT method, which I'll come on to in a moment. TC Investigator gets around some of these problems with contouring phase diagrams. It's developed by Mark Pearce and others. It's available from the website in Australia, and I've put the link to the well, I put the reference in the bibliography at the end of this presentation, and it's can be used with any of the 3.4 versions. It takes a completed diagram that you've already made, so it takes the input of DrawPD and various other files that you've generated that you've used to generate that phase diagram, and it basically does the job over and again for you, area by area. So it needs to know the areas and the assemblages, and it will then grid that output. And the good thing about this is it grids the normalized output results rather than any parameters that you've put in and asked to be calculated. So it avoids that H2O effect for the modes, and it produces diagrams like the ones on the right there. So for example, the mode garnet here, these are the actual output modes. Again, they're Mulder modes, but they are the actual output modes rather than the ones that I asked to be put in when I did the original diagram. So, okay, that's mode 1. Let's move on to mode 2, average PT. And so this is the inverse approach. And in the beginning, this was the primary purpose and major application of Thermocalc, I would say up to the late 1990s. And principles are outlined in that Powell and Holland paper 1994, optimal geothermometry and geobarometry. And the concept is that you should try and use all the compositional information and the assemblage rather than just one thermometer, one barometer. And what Thermocalc can do is find an independent set of equilibria among the end members that you, among the phases that you give it, and it will find a weighted best fit for a PT result, and it can attach an uncertainty ellipse to it. And so I've got some diagrams down here that highlight the geometry of that uncertainty ellipse, which is kind of obvious enough if you've just got two reactions. You can see the ellipse can be inscribed within the uncertainty envelopes of the pair of them. A little more complex when you have multiple equilibria, but the idea is that it can find a best fit, which will fit within the uncertainty envelopes of all or most of those reactions, and it'll estimate an uncertainty on pressure and uncertainty on temperature to go with that. It's an ellipse that varies in shape because there are inherent correlations in the data set you've been using, and they're reflected in a correlation coefficient, a correlation factor here, rho for 0.5 in this diagram here. And you can see here how the shape of the ellipse depends on the size and shape of the bounding rectangle here and the extent of the correlation in temperature and pressure that results from the correlations in the data set. And so a little diagram on the right that I'll come back to more than once actually, so I don't need to explain it in detail now, but it shows the patterns of shapes of average PT estimates for some Himalayan samples of different metamorphic grade. And so I'll come back to that on another occasion. So average PT is Thermocalc in mode 2. And the way you set up the problem here is to supply activities of end members for the phases that you're interested in calculating in that assemblage of yours. And obviously there are two ways of doing that. You can use Tim Holland's program AX or some other way of estimating external activities. In principle, it should be one that's compatible and consistent with the models that you're using. There might be problems with that. Perhaps we can discuss in more detail at some point, but that's one way of approaching the calculation. The other way is to directly use the coded solution models, in which case you'll need to turn your mineral analysis into something that can be represented in the X, Y, Z parameters. So in running the program, again, 3 files, essentially the same files that you might use for phase diagram calculation, but they've got slightly different functionality. There's the preferences file that points to the files you're going to use. The script file will contain either the name of the activity file you want to use. If you're using AX, it actually contains those activities themselves. If you're using method 2, you supply the XYZ composition variables in the script file, and then it goes to the XEOS to find the solution models that those refer to. The AX file, as I've just said, in method 1, it contains the activities that you're going to use, or in method 2, it contains the solution models, just as it would for a phase diagram calculation. And on the right here, there's some codings that I've produced using the latest version. So I've had to put in a value for the X parameter for a garnet here, 0.866. And within the program, then it's calculated the activity of almandine, the activity of pyrope from that in conjunction with the other parameters. And it's calculated from what I've given for the calcium content in a particular site. It's calculated an activity for the grossular, and then I've gone on calculated some results at average pressure at a range of temperatures on the basis of the independent set of reactions that it conjured up for me. So really, next you need to know what to do with a result like that. So again, on this slide, here's an average pressure result. It's actually for the same rock as previous, but it's the first run I did with it. And you might look at the results down here and say, well, okay, I've got some average pressures here, but the standard deviations on them are large. And the fit parameter, which ideally should be something
passes at a chi-squared test. So for something like this, it should be round about the 1.5 mark, and it patently isn't. So this is a bad result, and we might consider then excluding n members and improving it. And this rather ingenious matrix of diagnostics is something Roger Powell devised, and it looks very daunting to start with, but you can find your way around it by, first of all, looking for large values of this misfit parameter, and there are 3 candidates that come up here that look on the big side and might want to look at. There's ferroceladanite and paragonite and anite. Next thing you can look at is this hat column here. The hat matrix is something that tells you something about how influential individual n members are in your calculation, and that's highlighted. It's highlighted grossular here, but you'll see that grossular is associated with a very low misfit, so it means it's influential in a good way. Some of the ones down here, though, influential potentially in a bad way. They may well be ones that are causing that misfit, and those are potentially things that we'll want to get rid of in order to improve our results. Alternatively, here we've got one of our big misfits here associated with a small hat number, so that's not very influential. We might find that problem will go away as we deal with other issues. Last thing to look for is, did that result make a big difference to these deletion? Well, they're not exactly deletion diagnostics. I should have explained that. They are things in which, rather than deleting an n member and seeing the result, what Roger has done here is doubled the uncertainty on the activity and seen what the effect of that is. And this one in particular has changed the pressure and reduced the standard deviation very markedly and the fit very markedly. So that's the prime candidate for our first deletion. In fact, I ended up deleting paragonite as well, and then I got a reasonably good result. Okay, second little example here is example of plotting and interpreting results for actually a rock that I used in my PhD thesis very many years ago. So here are some activities which are calculated using AX, and again an independent set of reactions, so we can calculate that. We get, on the face of it, a fairly good result. Catch here is that this is a kyanite schist, and the results for pure H2O and the result for a fluid composition which is only 0.5 H2O, neither of them make a very good job of putting the PT conditions in the kyanite field. Moreover, the H2O saturated result lies above the wet solidus, and this is definitely not a suprasolidus rock. And that does underline the point that you can't guarantee that your average PT result is going to lie in the expected assemblage field. And if you're just using average PT, there's actually no way of knowing if that's the case unless you've already calculated the phase diagram. And I think other people will make that point later. Okay, a couple of other examples here. This on the left, there's an average PT example. It's the one we saw earlier. And again, some ellipses on here because we're regressing both pressure and temperature. And the different shapes are due to the fact we're using different mineral assemblages, and the constraints may be different. You can see that the constraints look to be somewhat better in muscovite-bearing assemblages than in suprasolidus rocks without muscovite. And I'll return to that again in the uncertainties session later on. On the right, we've got a set of data which are computed from local equilibria within clinoproxene, plagioclase, amphibole symplectites, breakdown product after opposite, and they make an array that we might want to interpret. And instead of regressing these for temperature as well, we're using an independent temperature estimate here, which is the Hornblende plagioclase thermometer of Holland and Blundy. And this is a procedure which is actually endorsed and approved by Powell and Holland as being something you might well want to do. And indeed, if you look at Thermocalc 3.5 now, you'll find that the average PT that produces the ellipses
not actually available for you anymore. So it seems that ellipses are on the way out. And so in the right-hand diagram, clearly I'm not using ellipses estimated in the same way as they are on the left-hand diagram. Right, now a word or two before I finish about mode 3. Mode 3 is one in which one might calculate all the reactions in the system. So basically here you give Thermocalc a set of phases and you ask it to calculate all the reactions possible in that system. It can do that at one level. If you ask it to do a Schreinermacher's analysis, it will then calculate the bundles and show you how they work in respect to each other. And you can also do it without Schreinermacher's analysis and simply see them all without the intersections. It'll give you the slopes and uncertainties on them. And that can be handy for checking the sensitivity of individual equilibria. I have used it for getting hints and implications about which end members are going to be useful and reliable and influential to retain, or opposingly, ones that are not really going to be very helpful and I might as well exclude from my average PT calculations. Main thing for me has been actually the possibility you can use this for discovering new geobarometers. And I guess the most significant one of those was the one I came across in 1991 for garnet clanoperoxene and phengite. So that's the garnet CPX phengite geobarometer, which is seen a lot of use in recent years, and it's been recalibrated now by 2 or 3 other groups of people, and is one of the very few geobarometers that seems to be useful in many eclogites. Example on the right is one for some mafic assemblages. Again, this is one for very restricted mineral assemblages that you might find again in these symplectites. Hornblende, CPX, plagioclase with or without quartz. And in this list, you can see this is just the top 5 reactions. You can see jadeite quartz albite that might have obviously popped up as a prime candidate with a small standard deviation and a low Clapeyron slope. But if you look at number 4, there's another one in here. It looks good. It's jadeite and albite and amphibole end members. So again, just 3 phases, and it's got a standard deviation that's almost as good and a Clapeyron slope that's almost as low as jadeite albite quartz. So that one could well be a good candidate. And in fact, when I put that on my website in 2003, Pierre Lenari has borrowed that for implementation in XMAP tools. And so by all means, go ahead and use it. Right, okay, time to summarize. So the strengths of Thermocalc in my view are this line-oriented and precise location that it'll give you for univariant curves and assemblage boundaries. I think also it's worth emphasizing, and I think some of the other panelists might agree with me, that it gives you learning opportunities about the properties of phase diagrams from hand-on construction that you don't necessarily get if you just use a free energy minimizer and press a button. Another advantage is that you can therefore do forward and inverse modeling from the same package. You can use your phase diagram, and you can also do the average P, average T, or average PT. Although this gives constraints on you, it also, in terms of the data sets and the solution models, it at least assures that you're going to be using models that are consistent with each other, and we hope they're also going to give you some accurate results. Okay, there are some disadvantages as well. It is much more labor intensive. The learning curve is quite steep, and as other people no doubt will point out, there's quite a large time commitment for using a complete diagram, for completing a diagram, let's put it that way. There's the onus on the user to decide which mineral phases to include, which means that there's an opportunity for error. If you miss some out, then you're going to calculate some metastable equilibria, and you won't necessarily realize that you've done that. G-minimization is possible. It's a bit limited in scope. It's not as efficient as a package that is in first and foremost a free energy minimizer.
It's tied to specific database solution models. Some of those solution models are still works in progress with known flaws, and that applies to even the recent ones. And so if you're going to use those solution models, that of course will apply to all the software that's deploying them. Some practitioners take issue with the way certain solution models are formulated. Other people might say more about that later. Program does crash from time to time. The error messages could be more helpful. And there are one or two elusive bugs that there's at least one that I know is still there, but fortunately it doesn't affect any results you come out. It's just a bit of a nuisance. So in practical terms, you might want a hint or two about what you can, about how you can go. Do some reconnaissance before starting. You probably will need to do some free energy minimization before you get going, unless you've got another model diagram closely similar to the one that you want to calculate that will give you some good hints about where to start. So you might want to use the do-g-min formation in Thermocalc. It can, on the other hand, be quickest to do a rough and ready run with another package, and then you might want to transfer and complete the diagram in Thermocalc. Firstly, for the graphical precision of the results. I put variety of output information. You can argue about whether you get more or better or different information from Thermocalc than you would get from another package, but there's a decent variety now. And again, finally, you will probably get a better understanding of the phase relationships. And so that's where we are. If you've done that, you've then got an equilibrium phase diagram, and you can use that for further petrological interpretation. And okay, it's an equilibrium phase diagram, but it is then the basis for you to use perhaps non-equilibrium insights to add your petrological interpretations to it. The diagram I've shown there is a case in point, which makes the point that you shouldn't really imagine that a single phase diagram will tell you everything you need to know about a particular sample. This one on the right here has a complex recorded history, which I've tried to decode and show aspects of its evolution, and a nice red arrow that goes all the way around. But you'll see, unfortunately, that the simplistic average PT result doesn't actually lie on the path. It's a spurious result. Anyway, much more of that later, and I hope if you decide to grasp Thermocalc, or if you're a user already, that you will be satisfied or have been satisfied with it. Right, okay, I stop there, and then we can show the list of key references there, and we can start with the Q&A. And I'm sorry if I ran somewhat over time there.
All right, well, I'd like to thank Dave for his comprehensive and also very balanced presentation on this very powerful software. So I think we'll move now into the question and answer period. There are a number of questions that have come in, and I think I'll turn things over to Jacob to pose those questions.
Thanks, Dave, and yeah, thanks, Dave Waters, for a great talk. I can start on the Q&A here. There was one nice comment that came from somebody. For anyone who isn't familiar with the Thermocalc software, if you go and Google Thermocalc, the top result will probably be some engineering software that is not what Dave has just spent the talk talking about. So use the links that he provides in his PDF. That was just a comment I wanted to make quickly. Okay, so somebody asked about, you talk at the start, Dave, about Schreinermacher's rules and exactly what these are, and perhaps you could provide some I don't know, references for places they could go and read about this before they try and calculate a phase diagram.
Schreinermacher's, yes. Now, there are some very old papers that will show you how the principles work. There's a paper by Zen, 1966, which I suppose if I'd been really efficient, I could have put on the key references here. However, if you go and look at the materials, particularly some of the older materials that Roger Powell put together for some of the old workshops, you can get those on the CERC website, which I had earlier. Let's see if I can go all the way back. See if I can go all the way back to that.
Yeah, I think that's right, Dave. On that CERC website, there's an entire section dedicated to Schreinermacher's. So for anyone who's interested in that before you start these calculations, that might be...
That's right. Yeah, yeah. CERC is an absolute godsend.
it's archived a whole lot of material that would otherwise have disappeared. And you will find, in addition to the Thermocalc section there, that's the direct link to the Thermocalc sections. But if you back off to the phase equilibrium module itself, you will find a lot more useful information in there. So I think that would be my advice. That probably is the best online resource that you can use now. I admit I had a little bit myself, not so much on Schreinermarkers, but on other things to do with phase equilibria and PT calculation on my own site, and that hasn't really been updated significantly at all since 2004. But I am hoping to get back to it at some stage and put some relevant new material on it.
Okay.
Anyway, for the time being, go to Circ.
Excellent. All right, well, I can move on to another question then. Asking about where can I get more help in constructing these PT phase diagrams? It seems like it's quite a complicated process. You know, where else can I go? I think you mentioned some tutorials and things.
That's right. Yes. Yeah. Now I'm wondering, since I'm still sharing a screen, whether I can find some links. But yeah, no, I don't think it will, because I'm explicitly sharing the PowerPoint here, so I don't think that will be very straightforward. But I say all of that useful stuff, the documentation from the workshops, you will find again archived on Circ. And in fact, I think this last link here actually contains some. So that contains the 1998 materials that were originally on a journal website, on Journal Metamorphic Geology website, that are now archived in Circ. And the other links here, the Thermocalc link down at the bottom of that page, that will link you to their archived versions of the workshop materials. If you hunt around on the modern website now, here also, some of that material is also linked from pages on the calculation methods. It can be a little bit hard to find your way around that new website, but just keep browsing, and ultimately you will find the links to all the old workshop materials. Roger Powell has some actually some very good notes on phase diagram calculations and their properties that he first put together in, I think, 1991, and have been updated in more recent years. And I think you'll find those very helpful.
Okay, great. So a kind of a more general broader question. For PT estimation, you presented these two methods that we can get at this information, the phase diagram and the AvPT. Is there a best approach for particular cases? Can you comment on that?
Yes, and I think the answer is that basically both approaches do have value, and you know, sometimes one will take you to you know, the answer you're looking for quite directly, and sometimes it won't. Point about a phase diagram calculation is that yes, the simplest way is simply to look for the assemblage you have in your rock and see if there's a field for it on the phase diagram. And to calculate the phase diagram, though, you need a bulk composition. If you have the bulk composition, chances are you also have mineral assemblage composite. You have compositions for the minerals in that assemblage. And so that opens both avenues for you. Anyway, if you calculate the phase diagram, you might find that there are sufficiently well-constrained assemblage fields for you to say, well, okay, my assemblage belongs in a relatively small field here, and that's it. And so if I calculate average PT, I'll get a big fat error ellipse that will be larger than this field, so I might as well go with the phase diagram, which is fair enough. The thing to factor in is that the phase boundaries, and I'll elaborate on this when we talk about uncertainties, the phase boundaries on diagrams depend not only on the basic thermodynamic data for the N members, but they also depend on any additional uncertainty that comes with the activity models and the uncertainties in the bulk composition. And so they have the potential to be large. And if, for example, your assemblage sits in a large field, and that large field potentially has large uncertainties on at least some of its boundaries, then you may well be distinctly better off using average PT. With average PT, the potential downside, I guess, is that you will determine a pressure temperature which doesn't fall in the calculated assemblage field. I showed an example or two of that already. Then you have to bear in mind that you said, okay, I put my mineral assemblages in there and my mineral compositions in good faith. And if I think this rock really is in equilibrium, then surely this result ought to fit in the correct assemblage field. And conceivably, in some cases, that's pointing to deficiencies in the solution models, or deficiencies in some other assumption that you've made about the bulk composition of the rock. So, you can't be too definitive about which one is best. And often I like to do both and compare them.
I think that's an excellent point. Yeah, if you have the data to do both, then perhaps you should try both. There were a couple of other questions here about what these uncertainties actually mean in the AvPT method. So people commenting that some of these error ellipses are quite large. How much information do they actually give? And I think you just talked about that from the comparison of using AvPT versus the phase diagram method. Matt Cohen asked a question here. Can you comment on this blanket assignment of errors to the activity models? You made this point that Holland and Powell don't want to underestimate the errors, but many times we're interested in the differences in PT between rocks, not their absolute PT condition. If I get this large error on AvPT, I can't assess how tightly different equilibria intersect.
Absolutely. No, that really is a key topic and a key question. It's not easy to answer though, but I will be returning to it in the uncertainties presentation. So don't worry, there will be more about that. Yes, if you want to find out a bit more about the way the way Powell and Holland formulate those estimates of uncertainty on the activity calculations, then they do explain that their initial model in a quite full and comprehensive way in the 1988 paper, when Thermocalc was introduced. So do go and look at that. It's got two aspects to it. One is that you can make some simplifications because normally for a particular mineral, there's one type of site which probably contributes most to the uncertainty. And so you might as well concentrate on figuring out what the uncertainty is for that site. And for biotite, maybe it's the sites that contain the iron, magnesium, and the aluminium in octahedral coordination. And so there are three of those. So it's a site with multiplicity 3. So we'll estimate the uncertainties so that kind of works. Then there's another thing that you might want to build in, which will stop you giving too much weight to uncertainties which have very small values, because they're likely to be more uncertain in their own right, and that's also built in. And that sort of assumption was modified a bit in the more recent application, I guess in 1998. Well, it was, and there's mention of it and more discussion of that in the 2008 on thermobrometry paper. So that's the other place you can look for a bit more information about those uncertainties. And yes, I have to admit they are uncertain uncertainties, and it's quite difficult to make a sort of hard and fast criterion by which you can use relative uncertainties and say this PT is actually different from that PT. But that's something that we can talk about in the uncertainties session later on.
Excellent. Yes, Dave will be giving a whole talk on uncertainties on Wednesday, whatever time zone you happen to be in, I suppose. I shouldn't say morning. Okay, so that I think that people again asking about AvPT and your when you're trying to choose the assemblage that you should include in AvPT, what do you do if you have phases with multiple compositions, multiple feldspars, etc., etc.? How do you go about deciding what you should include?
Is the question asking about pairs of mineral compositions that might be in equilibrium with each other across a solvus, or just having lots of different compositions in the rock?
Yeah, I suppose
some kind of spatial disequilibrium or whatever.
Yeah, so yeah, okay, so the second would be something that I'm sure Pierre will deal with on Wednesday. The first would be, I think, is what they're trying to get at in this question. I'm not quite sure.
Oh, okay. Yeah. Well, it's that there are ways. It can be a little bit tricky to resolve things that are sitting on either side of a solvus. And I mean, worst case scenario is that you've got amphiboles that where you're down at low temperatures with in the miscibility gap, gaps plural, between sodic and calcic and other things at low temperatures. In a way, we need someone like Paul Starr to help us with things like that,
yes.
as you and I know, Jacob. And that is tricky, particularly where there are miscibility gaps that are going to open up. Just you can solve some of that by trying to fix your. I'm not sure how easy this is to do in average PT, but you have to try and fix your starting guesses so that they will end up on the right side of one particular solvus or another. One trick you can do with feldspars is to use pure end member albite, which is a separate phase, along with the Planchet-Claise solution model, and that does, surprisingly, it does a reasonably adequate job of finding the at least one arm of the peristirite miscibility gap for you. And I do actually use that from time to time if I'm interested in the transition from green schist to amphibolite and want to see where you stopped using albite, and for a little while you get the coexistence of the two, and then albite disappears and you get the Planchet-Claise.
Okay.
Otherwise, it's a matter of just looking at all the mineral compositions and trying to find something that's going to give you a nice cluster of analyses that you can average and say, this is my composition I'm going to use for the equilibrium calculation.
Okay, Dave, we'll have one last question before a short break and we move to our kind of open. And this is, again, average PT related. Somebody asking here that if you go on the HPXEOS website, there's the application of AvP to gabbroic rocks in this recent Zaberna paper that I think Eleanor Green is on. Are there disadvantages of using this algorithm in igneous rocks compared to metamorphic rocks? Do you have an answer for that? Or?
I don't actually, because I haven't been into the igneous applications of the modern data sets yet, and it's that's my deficiency. I just haven't had time to look into that yet. I'm still stuck in the metamorphic realm.